In this example, we're going to solve a 3x3 system of linear equations, and we're going to see how we can combine the rules we've seen earlier to find the general solution to an example like this. First step is to find the eigenvalues, because what we're doing here is making an assumption that x of t looks something like e to the rt times some vector, and that led us to the subbing in here, getting r times v equals a times v eigenvalue eigenvector equation. So let's go looking for eigenvalues to find out what r could possibly be. To find these eigenvalues, we set the determinant of a minus ri equal to 0. And here that's 1, 0, 0, 2, -1, -2, 3, 2, 1, and negative r down the diagonals, like so. Now to do the determinant of a 3x3 matrix, I like to do the cross multiplication approach. Again, any technique that you know is fine. What we're going to do is copy these two columns here over to the first two columns here, just as placeholders. You can also do it with submatrices if that's what you've learned. They both give the same answer in the end. So what we're going to do is simply multiply down the diagonal here. That's going to give us 1 minus r times another 1 minus r. Careful, I made a mistake there. So it's just positive 1. And another 1 minus r. Then the next diagonal is actually 0. As soon as we have a 0 factor, it goes away. And we have a third 0 factor as well. Then we're going to subtract the up to the right products. So 3 times something times 0. 2 times -2, and the negative's just out front, so we're getting the negative of it later on, 1 minus r, and the last product is also 0. And that gives us our characteristic polynomial. This entire expression here altogether is the polynomial we're looking for, and if we expand this out in stages, we'll have 1 minus 2r plus r squared times 1 minus r, so putting two of those together. And at the end of the day, we're going to have minus, we're going to have plus 4 1 minus r's. Then we'll have negative r cubed plus 2r squared, so multiplying this r into each term, minus r, and then multiplying the 1 into each term, we'll add an r squared, minus 2r plus 1, plus 4 minus 4r. Negative r cubed. We've got the r squared terms there, so we've got 3 of those. We've got 3 r terms here, minus 3 minus 7r. And last but not least, the constant terms, which give us plus 5. And we want all of that to equal 0. Well, if that's the case, again, it's a cubic. We start doing some guessing. And because we're not going to be too cruel to you, if we look at these values, we've got 3 and a 5, that's an 8 and a minus 1 and a minus 7. Hey, if r was equal to 1, we'd have minus 1 plus 3 minus 7 plus 5, that equals 0. So r minus 1 is a factor. And then we can combine that and this to get r minus 1 as a factor. We'll have negative r squared, and we'll have, to get the 5 at the end, we'll need a negative 5. This will give us plus r squared, we need plus 3, so we'll have plus 2r in the middle. And that, let's make life a little bit easier on ourselves. We'll multiply through by minus 1, which we can do on both sides without changing the right-hand side. And that last expression there, we'll pretty much need to use a quadratic formula. But if we do, what we're going to end up with is r equals 1 plus or minus 2i, or 2 times the square root of -1. So we also get complex roots here. In fact, it's a complex pair of roots. But that's fine. We now have a real root at r equals 1 and a complex pair of roots. So we can just go ahead and build our solutions using all the techniques we've seen so far. Let's let r1 be 1, and that's the real, distinct, there's no other solution like it. That's an eigenvalue. And what we want to do is find the eigenvector for it. And that comes from the matrix equation A minus Ri times V equals the 0 vector, or in our case, subtracting 1 from the diagonal, we have 0, 0, 0, that's nice already, 2, 0, negative 2, and 3, 2, 0. All of that times V1, V2, V3 equals the 0 vector. And right away, we can jump to our solutions if we like. Let's call these two interesting equations 2 and 3. We'll start with 3. That gives us 3v1 plus 2v2 equals 0, or v1 is equal to negative 2v2 over 3. So what I might want to do here is pick v2 to be a multiple of 3 to make this work out nicely. So I'll pick 3, and that will lead to v1 being negative 2. Again, we can always choose one of these arbitrarily because one of the equations isn't constraining v1, v2, v3. We can then go back and take a look at 2, which tells us that 2v1 minus 2v3s equals 0, and v3 then is going to equal v1, well, we said that was negative 2. So this is going to give us eigenvector 1 is going to be negative 2, 3, and then v3, which is negative 2 again. Perfect. So that tells us as well that one solution is x of t is equal to e to the eigenvalue here, 1 times t, times the eigenvector, negative 2, 3, negative 2. And we're good to go. Now on to the other eigenvalues. With our complex conjugate pair of eigenvalues, we just need to find the eigenvector for R2, which is 1 plus 2i. And the same thing in terms of equation setup, we have r minus I times v equals the 0 vector. What does that look like in terms of our vector? Well, you get 1, this one we'll write out explicitly, minus 1 plus 2i, then 0, 0. So it's a big looking matrix by the time we're done. 2, 1 minus 1 plus 2i, minus 2, and 3, 2, 1 minus 1 plus 2i, times v1, v2, v3. All of that equals the 0 vector. Again, with complex roots, it's not necessarily obvious what cancels with what immediately, but we certainly do get a pattern of 1 minus 1s. So down the diagonal, we simply get minus 2i's, 0, 0, and 2, negative 2, 3, 2. Now this is actually nice, and maybe a bit surprising. This first equation here tells us that negative 2i, remember this has to equal 0, 0, and 0. So the first equation tells us that negative 2i v1, that times v1 has to equal 0. So we actually get a freebie here, v1 has to be 0. With that being the case, we can focus in on the remaining equations, and either 2 or 3 is fine. They're both going to give us the same answer in the end, even though it might not look like it at first glance with complex numbers. But we can work with this v2 and v3 to see that negative 2i times v2 minus 2v3 equals 0. We ignore the v1 coefficient because v1 is 0. From this stage here, you can do whatever you like. I would just pick v2 to be something. Let's let v2 equal 1. Then we get negative 2v3 is positive 2i's, just bringing this over, and v3 is going to be negative I. So our eigenvector here, number 2, is going to be 0. The 2 is a second component is a 1. The third component is negative I. And we can write that as 0, 1, 0 plus I times 0, 0 minus 1. And that is enough to build our solution. We'll build the solution for this on the next page using the formulas in the upper right here. With our eigenvector and eigenvalues, recall that the scalar values are the ones that go into the exponential and cos multipliers, and the two vector components are what go into the multipliers for those. So we're up to solution 3, so we're going to call it that. x2 as a solution is going to be created using this formula, e to the t times cos of 2t and sine of 2t. Those are the first ingredients in terms of the function. Then we have the actual vector components, 0, 1, 0, and the b, second part here, goes with the sine term. And x3 is e to the t, same basic functions, just the order is reversed. And then we use the same vectors, so sine times a, 0, 1, 0, and cos 0, 0, negative 1. With all of that, we get the general solution, which we will not rewrite in all its glory, but x of t will be the linear combination, key thing is the idea here, the linear combination of x1 from the real r value and x2 and x3 from the complex r pair there. So it'll be c1 e to the 1t, e to the rt, times the eigenvector that went with that, negative 2, 3, negative 2, plus c2 times x2, plus c3 times x3 of t. And where x2 and x3 are the solutions we've written out here. And that's our general solution. So while at times the calculations can be tedious, the actual process is very straightforward. And if we skip over the by hand step of finding eigenvalues and eigenvectors, constructing these solutions is actually very straightforward conceptually. So focus on that. Don't get too lost in the minutiae of computing eigenvalues and eigenvectors. Or after you have dug into the eigenvalue and eigenvector detailed calculations, take a step back once you have the solution to see what does this combination mean in the context of your problem. That will make more sense when we start looking at applications.